Okay, so let's get started so that we can get back to lunch on time. So yeah, I kind of want to continue on from where we left off, more or less, and then go to system F. So this was just simple types. I want to say something about polymorphism. Okay, so just a quick thing, right? I showed some corollaries before, which was like, that's what we actually care about, is just like a special case. Sort of like another quick exercise, warm up after the coffee break. Let's do another corollary. So corollary, right? So this one, if it's closed, and I know that expression exactly as it exists is reducible at some particular type tau, right? So what if tau happens to be bool? It might be bool. So I know something a little more specific again, right? So it was generally the case that every reducibility definition thing only had terminating stuff, but the specific definition for bool said a little bit more than just that. What's that say? It's not just that it terminates. What else does it say? Right? So if I've got an expression in fancy square braces of bool, what do I know? It terminates with a bool, right? So another corollary of this, like just saying what if that's bool, is that if I've got a closed expression of type bool, then I know it lives in the meaning of bool, and therefore there must be a real Boolean value that it evaluates to, that it becomes after running it. So then there is a Boolean, a Boolean B, I believe I called them, right, which is true or false. So there's a value true or false. Such that E reduces in many steps to B. So I can't say something more specific, and it kind of wouldn't make sense if I could say something more specific. I can't say that E is exactly true or false because clearly I can type check more than that, right? I've shown some examples, like many things I say are of type bool, but the thing they've got in common is that they definitely have to, at the end of the day, become a Boolean value, right? This is just a quick consequence of that thing, and I derive it based on the way I defined these logical relations. So what I'm saying here is not like the only possible thing you could do, right? And it's not like this is the logical relations for the simply type lambda calculus, end of story, right? It kind of, there's a hint I baked in termination. You could do this different ways depending on what you're doing, and that's fine. Really, it's you define these to get the results you're after, and a correct logical relation is whatever gets you what you're trying to do, right? It's sort of like this, at least I take this pragmatic view on them. It's not like what is the meaning for functions, it's what's the meaning for functions I need in order to show something, right? Okay, so yeah, so this was simply type lambda calculus, so only functions and basic types. So what happens when we add in polymorphism, right? We had this extra type for all alpha.tau, which meant that you could instantiate alpha with any type at all in my language, and then I get a specialization of some generic algorithm at that type. That's the idea. So, well, no surprise if I want to show, I'll do termination again as sort of the thing I'm proving to continue on from before. You're clearly going to need this kind of setup, or maybe something else. Maybe there's some other way to do it, but the naive sort of let's just go and prove it doesn't work. You get stuck for exactly the same reason, and we'll still have functions. So exactly the same kind of place. But what I'll do here is add for alls to the language, because I want polymorphism, and let's see, well, how to define it. Because like in some sense, all the other stuff was pretty generic. The only time I really cared about the type of stuff was when I was proving the fundamental lemma. I get to a typing rule involving something like functions, and I have to talk about what they are. Or I'll get to a typing rule that has something to do with for all, and I have to say something about what that does. But like this definition doesn't care what kind of types I have, and these other properties don't care. So it kind of gives you this methodology where at least like different language features are, like they don't interact in weird ways. Right? I can just like talk about this is what functions are. And I'll only bring it up when I'm actually talking about functions. And when I'm talking about Booleans, I don't have to say, oh, wait, but I've got some other thing in my language, and that impacts what the meaning of a Boolean is. All right? So it'll work if I just kind of define what the meaning of for all is, and then you just kind of extend that big fundamental inductive proof with a couple more cases, which say, what happens when I type check some sort of for all thing? Okay? So step one is define what does it mean when I've got a for all? What is the reducibility meaning of for all? All right? Okay, so let's just try. So another general idea, if you don't know what to do, just try. Because if you spend all your time worried about if you're doing it right, you'll never get anywhere, right? The only way to get somewhere is to learn from your failure. So don't be afraid. And so it's just another case. What happens, let's just do it, right? Let's just say, what is the meaning of a for all? Okay. Let me make some more room. This is E applied to E prime is in tau 2. Now, this goes over here. The meaning of for all alpha dot tau, what's that going to be? And well, in system F, that's what we're doing. For alls looked a lot like functions. They just abstract over types instead of values. That was really the only difference. So to start, how about I try to define for all kind of like this? What happens, okay? So what does a generic thing look like? So what captures the essence of being a reducible expression of type for all alpha dot tau? So it should be terminating because that's what I happen to be trying to prove at this moment. So I'm engineering the whole thing around that fact. If you don't care about termination, then leave it out or do something else. Okay? What else? So what do I do with a generic thing? So here the question is, what do I do with a function? And the answer is you call it with an argument. That's what you do with a function. Right? What do I do with the for all generic thing? What was the one operation? What was that? Specialization, right? It's pick a type, any type, and you can like plug that in for alpha. That's the idea. Okay, so let's just try to do that. So here it was for all alphas. Here I'll say for all tau prime is some sort of type. And then I specialize E for tau prime. Right? Okay, so E specialized at type tau prime. And where should that live? So for a function, the results of an application lived in the results type area. Where does this live? So it lives here where I plugged in tau prime for alpha. That was kind of like the typing rule. Specialization plugs in the specializing type for the variable. Okay, so that means this should live in the meaning of reducible things at type tau prime for alpha. Okay, so how about that? Does anyone have a problem with this? Does anyone have a problem with this? Is this a good definition? So, I mean, the two things you care about is, does this definition do what we want it to do? And we kind of find that out by trying to prove things with it. But also, does this definition do anything at all? So if you've done a lot of induction in the past, you might start to get spooked out, which is this a definition? Have I really said something? And I kind of said this earlier on, right? That I said I was going to define the meaning of these fancy square braces applied to a type by induction on that type. Right? So, okay, fine, I can just define what a Boolean is outright. I can define tau1 arrow tau2 by induction because I know what the meaning of tau1 and tau2 are. To define the meaning of this, I'm asking for the meaning of that for any type. Is this at all an inductive argument? So we've got to vote for yes. Does everyone agree? We're just like, good? Anyone say no? So yeah? Was that a no? That's a no. Okay, so we've got one yes and one no. Two no's. Okay, so we're starting to come down a no, and I'll be another no. And the reason is, right, so how does induction work? And it's kind of like, writing a recursive program. This definition itself like terminates and gives me a real mathematical statement by induction because I only ask for the meanings of sub-expressions in the type, right? Sub-parts of that tree. Is tau, with tau prime for alpha, where tau prime could be absolutely anything at all, is there any way where that's like a sub-piece of the tree that is this type? I mean, it contains some, but then I like totally modify it and grow it in weird ways. And so I'll do the special case, which is what if I have the meaning for all alpha dot alpha, right? If this is well defined, this should be just one of the many cases of this definition. Unrolling that, it says that it's any terminating term such that for all tau prime, E applied to, or all tau, E applied to tau is in the meaning of tau, right? Like I have to know the meaning of every possible type I could have written down whenever I encounter for all. This isn't really induction. So this isn't really an inductive definition. So if I say that, I haven't defined anything at all. Yep?
You can just go into the subtree, tau and tau prime, and get it worked out. I mean, it's a substitution.
Kind of.
It's a subtree.
Right. So I know the meaning of tau modulo alpha. I don't know the meaning of that yet. Here's the really problem part, right? One of the things this could be, right? One of the cases is what if tau is equal to for all alpha dot alpha? So in this sense, to say what is the meaning of for all alpha dot alpha, I have to already know what is the meaning of for all alpha dot alpha, right? It's not just that, but there's this really vicious circularity that's not good. So I kind of have to define the meaning of for all without, and I have to plug in something for a type, but I don't yet know the meaning of all types because we're in the middle of doing it. And this is the problem. It's this vicious loop that doesn't really let us get started, right? And so this is the problem of System F. And the reason is it's a type of polymorphism that's known as impredicative polymorphism, if you've heard of this word before. And the idea is that when I say for all, it's over all types, which is the set that includes the quantifier itself. Right? So this for all alpha dot tau ranges over, among other things, itself. It's not like a kind of for all where I define some sort of domain and then that's done. That's one definition. And then I quantify over that, and that's some more stuff. And then maybe I could quantify over those things. It's like I'm quantifying over the domain that I myself is contained in. And that's the tricky part, right? Okay, so what do we do? Basically, this isn't an inductive definition, so this doesn't work because I haven't actually said anything interesting, really. I'm just I hope that's the case. It should be the case, right? That's a property I would like to hold, more or less, but it's not a definition of what something is. It's that distinction. It's a little bit hard to wrap your head around, but that's kind of the problem you want to avoid, is this vicious circularity. So how do we untie the knot, which is that I want to quantify, I want to say what the meaning of types are by quantifying over what it already is while defining the meaning of those things, right? How do I cut that knot? And or how do I untie the knot? And the answer is you just completely cut it in half. And, oh dear, I kind of don't have room here exactly. But, so remember this picture. Right? Ultimately, I cared about terminating stuff. And I want to relate that to type stuff. And I couldn't do that directly, so I put a middle point. And that kind of was part of the picture. And now I'm kind of in this situation again where I want to do something and I get stuck. And like my induction doesn't work. But it doesn't work for a bit of a different reason. It's not a problem of, well, it kind of is a problem of the inductive hypothesis. It's kind of like not strong enough in maybe some way. And so what am I going to do? I'm going to put another middle point in. And there's going to be another sort of division in my world of nested, Russian nesting dolls, pretty much. And so this is the thing that I'm going to call a candidate. And so what's that? So right, the outer box was all expressions I could talk about, the set of all expressions. Inside of that was this. Inside of that is the set of all terminating expressions. I'm just adding some side condition to it. And then inside of that was reducible stuff, which was this really like neatly defined inductive definition that was based on programmed behavior. And each like reducible thing was give me a type and I will define a set of expressions that are reducible at that type. And the idea, and those for each of those types, like for Boolean or any function type, they had some essential properties, right? What was the essential properties? I don't have the theorems up here anymore. Yeah, these were the essential properties. Like my proof only worked because of those two facts, right? At the end of the day, I can only prove termination if indeed the reducibility sets of every type only contains terminating stuff. That's what I'm trying to do. And I also needed this expansion property, right? That if I expand the reducibility meaning of some type, it's the same thing, right? Everything that I could get by reduction or by expansion is already in there. And that was essential for proving my fundamental lemma. If I didn't have that fact, I don't actually say anything. Okay? Right, so the first one was to make sure that reducible types are in the terminating set, and then vice versa, that well-typed things are irreducible. So that was the properties of the meaning of any type. So what I kind of want to do, and it's related to that question of you don't know all the well-typed terms are terminating, and so how can you say that something is terminating? But terminating is just a property of an expression that I can say an expression has. So the set of terminating things is well defined before I say anything about type checking whatsoever. So the idea is, can I like come up with a set that's all the things that might be an interpretation of a type. I don't know if it is an interpretation of a type, but it has the essential properties that I need in order to do what I'm doing. Right? So here it has those two facts. And I'll call that yeah. Let's write it over here actually, so it's visible. So I'm going to define something. So I want to say, it's a definition. I have to say, if I want to interpret types, what might that interpretation be without talking about specific types? So it's got to be terminating, and it's got to be expansive. So I will now say that a reducibility candidate is any set of expressions C such that the expansion of C is contained within C, which is contained within the set of terminating stuff. So, okay, first question. Is that a definition? Right? Do I have a weird vicious circularity there? So we should be very confident about that, because that's what I'm trying to avoid, is some weird, like, infinite loop in mathematical definitions, which means I haven't done anything. Right? So does that make sense? So, well, okay, I just need to talk about sets of expressions. Those are things. I can talk about sets of expressions. And I've already defined what that is. The expansion of some set of whatever, I don't care. I've defined what that is. And so this is a definition, right? There's no reducibility candidate does not depend on the definition of what reducibility candidates are. Right? So does that make sense? So, like, step one, we've defined something meaningful at least. Huzzah. But then what's the point of defining what this is? It's sort of, I've defined this space where any definition of some type tau has to live in for me to do what I'm trying to do. So it's like I've laid out this domain where every interpretation of type has to live here, because that's the point. And we could rephrase these two lemmas as another lemma, which says, lemma, for every syntactic type tau, the meaning of tau, and I'll say here, or I'll just say is, a candidate. So this lemma is exactly the same thing as those two put together, because I've defined reducibility candidate as the two lemmas I need in order to prove my fundamental thing that I'm doing. Okay? So I'm just kind of like shuffling around definitions and things here. Well, okay, so now let me go back and try again to define what this is. And the problem, well, there's kind of like a boring technical problem of kind of like what you were saying, like say about the meaning of tau without like doing the substitutions. That's like one boring technical problem. But the hard problem is, okay, fine, but then what do I plug in? Because I still like can't do this. So I'll show this. So I'll try here to repair this way. So this first, I'll say here, and what I'm going to do, and because I've got variables as well, I should also say what to do if my language of types aren't just bools and arrows, but I also have type variables. What happens if I try to ask for the meaning of a type variable? What is the meaning of alpha? I don't know. It depends. What do you think of alpha is? Right? So here's the trick, and this is also, a lot of this has the feeling of denotational semantics in programming languages. I'm just like, the denotation of things is more syntax. But the methodology is all the same, and that's like kind of what logical relations are. How do you do denotational semantics without denotations? So what do I do here? The idea is, if you need to know the meaning of a variable, that's not defined, so just pass in an environment that tells you what the meanings of variables is, and that's someone else's problem now. So this is the punt. It's someone else's problem. So the meaning of alpha is whatever this sort of theta thing alpha is. This is going to be like what corresponds to when I was type checking and there was a bunch of free type variables. You also have to like decide what you mean by those, if there are some. But that's well defined if theta gives back something sensible for alpha. Okay, and then Well, okay, I'm going to have to extend now all these cases with I'm threading around an environment. So if I ask what's the meaning of bool depending on how I interpret variables, I already know what that is. It doesn't really depend on that. What about functions? Well, when I plug in substitute for type variables, I just plug it in on both parts. So you just thread this around. There's nothing really that interesting here. It's just bookkeeping. Right? So whatever the mapping is, just use that. But here, this is interesting, because I actually want to plug in something for alpha. This is one of the problems I wanted to avoid. I don't have to plug in something directly for alpha, just like add it to theta. So I can ask for, what's the meaning of tau? And that's a good, well-defined thing. I know what the meaning of tau is, as long as I can plug in something sensible for alpha. Okay, so what about this? I'm going to say theta, and then when you run into alpha, what should I put? And so I could say this. So this is like literally what the typing rule for all was, which is pick a type, and then the instantiation, the generic type where I've now specialized that type for alpha. So is this well defined? Yeah.
It's the exact same self-referential.
Yeah, I've kind of like done the boring problem, but I still need to know what the type of, or the meaning of every tau prime is, right, which might be that, right? This is still viciously circular.
And once more, how can a variable alpha like store all of like the meaning of
well, that's kind of like right here. That's a problem for theta to figure out. So it's got to know like all the meaning. Like, so if you say, oh, alpha's bool, you plug in that for alpha. This is kind of another problem, though.
Set R substitution is
yeah, and so
say that like that set is the substitution itself.
Right.
That notation suggests.
Well, okay, and so the idea is for this theta thing to make sense, I kind of have to know what I'm giving back. What does theta have to return for this whole setup to make sense? So it's got to be a set of expressions, right?
Why is it a set of expressions?
So the meaning of
context.
So the meaning of a type is a set of expressions with some properties attached. The meaning of alpha is then theta applied to alpha, or the what alpha is in theta, which means that theta's got to be some sort of map variables to the meaning of a type. But where do the meanings of types live? Right? You have to ask where things live. And really, so I want to like be able to plug in bool for alpha or bool arrow bool. So it's some set of expressions such that, each of those expressions is terminating, and the whole set has this expansion property, right? It's closed under expanding. Anything that might reduce to one of those things is also one of those things. So that's what this is. Another way of putting it is that the theta component is a mapping of what, right? So each of these is now parameterized not just by where it's the main inductive thing, but this extra mapping. And what is it going to be? So this is a mapping from type variable to what? And I'll call this CR, where CR is the set of all reducibility candidates. Set of all reducibility candidates is CR. In honor of Girard, who called it CR because he's French, and therefore it's candidates of reducibility rather than reducibility candidates. So if you see that, that's probably what that means. So is CR well defined? Well, if this predicate is well defined, then that is, because I can take the power set of sets of expressions. So I just winnow out the bad ones and only keep the ones that might describe a type. So that's what theta is. It says for each type variable, give me something that looks like a type, that looks like the meaning of a type, to say that what alpha is. So that's that part. So do we kind of understand what's going on here? Yeah?
Yeah, just a clarification. I'm a little confused by the notation in that for all. I think that there's a lot of line of it, or you apply.
Here? Oh yeah, so I'm extending a mapping. So theta comma this slash means it's the function that when applied to alpha returns this, and when applied to anything else just asks theta.
And that doesn't happen. That.
Yeah, so my notation here is theta with some c for alpha. If you ask what alpha is, you get back c. And anything else, theta with a c for alpha. So this is like extending an environment. So if I ask for some beta, I just get back theta applied to beta if alpha is not equal to beta. This is kind of like a detail of I've got environments and mapping. So it's a function. I can always override one result of a function. I can decide if two type variables are the same because they're like different strings or however you represent them. So it's like are alpha and beta different strings? If you just ask theta what it is, but if you ask for alpha, then return this instead of whatever theta might think it is. This is just extending an environment which is represented as a function. Does that make sense? Right. So the extension is fine. The problem is I'm asking for the meaning of tau prime, right? So I'm not allowed to apply fancy square brackets to tau prime because that's not really found anywhere in here necessarily. It's not like smaller than the type I started with, which is kind of like what powers induction. And so this is like a nice technical device that really isolates the problem, which is I can't ask this question. I can pick some random syntactic type. I can apply I can apply my generic algorithm to specialize at that type, but I can't ask what the meaning of that type is. That's the core part of the problem. So, well, what am I going to do? And, well, the answer, which is rather tricky, but what I'm going to do, if I can't do the right thing, because that really captures what the typing rule said, if I can't do the right thing that's allowed by the laws of type checking, then I'm going to cheat. And the answer is you completely lie. You make a just unashamed, bald-faced lie, and then get away with it. And that's the idea here, is that we're just going to give up on like thinking about what's the real well-typed things and just whatever, I don't care. Because it doesn't really matter to me. It's about what programs do, not that they're well-typed. That's like a separate issue. So I'm still going to say, all right, pick some tau prime, which has got to be a type, because I have to say something about your generic thing. Which instantiation do I want? Pick some other completely unrelated reducibility candidate. So some C, which is in the set of sensible things which might be a type. Okay, the set of, this is like all potential meanings of types. And then I'm going to say that E, instantiated at tau prime, has to live in the meaning of tau, interpreted or evaluated in an environment in which theta is extended with C for alpha. Okay, so question one, we've been trying to define what the heck this means. Is this a definition? Do I have vicious circularity anymore? The answer is no, because the only recursive call I ask for when I'm asking for the meaning of things is tau, which is exactly the smaller type found within the quantifier. So this is an inductive definition. Do we kind of see where we've solved the main problem of vicious circularity? This is no longer viciously circular. This whole thing is now a proper inductive definition that does come up with a statement in mathematics. Okay, so, yeah?
Wouldn't you know what the meaning is of all the C's?
I don't, because we agreed already, before I even talked about what actual meanings for types are, I laid out a space of what might be potential meanings for types. That doesn't say anything. Like, this is already a well-defined definition. Never talks about that whatsoever. Square brackets don't appear here. Therefore, this, like, in your Coq proof, if you think like a theorem prover, I've defined this. It's defined already. Now I want to go and define that. Right? So this is, and it's kind of like I go try to define it. I see there's a circular problem, so I step back. I'm not really defining that yet. I lay out a space that I want to work in, and then I'll show that I actually worked in that space.
So it's like CR is taking the place of your inductive hypothesis. You're saying that
Kinda.
I already know.
Yeah. The set CR already exists, and now I want to define a meaning from types after I've defined what CR is, such that, i.e., the meaning of tau has got to live inside CR. So I already know what CR is. I want the other thing to hold. Okay? So that's kind of like the order of definitions. The definition of what a candidate is comes first. The definition of actual reducibility comes second. So this is like potential things I might have, and then the actual stuff I do have. Okay. So hopefully we understand why this is a definition now. If not, you can meditate on it a bit, and I'll still be here in the following weeks, so you can ask me if it's still troublesome. But the thing that should worry you is that I'm lying. This is like a definition of false advertisement. Why is that? So it's like, okay, pick a type, tau prime. I'm telling E that I want to use it at tau prime. Like, that's my specialized instance I would like to use. Then I pick some reducibility candidate. That's just like some well-behaved set of expressions. Does that have to have anything to do with tau prime? No, there's no reason why these two things have to be related in any meaning whatsoever. There's like no requirement that there's any connection. It might be that after I've defined this, I could hypothetically pick the meaning of tau prime. It's not part of the definition, but it might so happenstantially be the case that I say, like, I want to use you with alpha equal to bool, and then I'm going to plug in the meaning of bool. I'm allowed to do that, but I'm not required to do that. That's why this is total false advertisement, because I can say one thing and do another. So the definition of the meaning of a for all, and this way I'm setting it up, is totally duplicitous, right? So the worry is, okay, that's fine. Can I now prove my fundamental lemma? Because this is like way weird that I can do this. And the magic of this whole thing is that I can get away with it, and no one catches me lying. So that's the magic, and that's like sort of the secret thing that makes parametricity what it is, or it's why it's a strong thing, right? In some sense, because I have to do exactly the same thing, right? E can't change its response based on what you picked for alpha. It has to be totally blind to the instantiation. There's not like, well, if you picked bool, then I'll negate it, and if I picked number, I'm going to add 10 to it, and if you picked some other thing, I'll do this, right? I have to do the same thing no matter what. So it doesn't matter to me whether or not you're honest, right? It's a huge requirement on the elements of a for all type that they have to be so well behaved they cooperate with liars. Okay, so the proof that it makes sense is that we can actually prove the fundamental lemma, right? That's like the point. So, question, is the meaning of every type a reducibility candidate? So we can kind of do the quick induction in our heads. Is the meaning of reducibility theta? Yeah, we already knew that. What about an arrow? Yeah, it's the same thing. What about the variable case? Yes, because I constrained theta so that it was only allowed to give back reducibility candidates. So you need that as a requirement or it doesn't work. And that's why, because when I come to like the base case of a variable, I have to know that theta doesn't like break everything. And then finally this, right? Do I have termination? Is everything in a for all terminating? Yes, by definition. Does it have expansion? Yes, for reason as for functions, that I'm allowed to reduce within E even when it's instantiated. Therefore, if I step to some other place and it lives here, then because this has the expansion property, for all has the expansion property. So for functions and for all, they inherit expansion, whereas for bool, it just has it outright by definition. Does that make sense? That's the do I contain enough stuff requirement, and the am I terminating is do I not contain too many things. Okay, so let's do the rules. And conveniently, I've got something that's almost the right thing. I'm proving the fundamental lemma, which said, if I have a derivation of some judgment, then the meaning of that concluding judgment is true. So I have to update. Sorry about that. I've got to update this stuff over here because for polymorphism, the judgments were extended. If you remember, we had to say some stuff about free type variables in addition to free term variables. Okay. And so what are those going to be? So I will say that here, right, it's sort of, I have a big theta and a gamma, right? And so one of the things I said was that it's a substitution such that everything you plug in for variables live where you said it did, right? But to ask this question, I need to say what the free type variables in it mean. This is kind of like we're doing all this, back and forth about plugging in for free variables. So I'll say, well, just assume you've already got a meaning for free variables, which is a bunch of candidate definitions for whatever you have. So it's a substitution where, I'll rewrite this over here. The substitution of sigma for x has to live in the meaning of tau with respect to little theta. And then, what else? Right, so this is a combination of both what to do for free variables, what to do for free type variables, and for all alpha in big theta, well, the substitution should plug something in for alpha. And that's just got to be some sort of type. I don't really care what you pick. So basically, I have some syntactic substitution environment, which is defined for all free regular and type variables. I don't care what you put for the type variables. That's irrelevant. But for like a value, it should be a sensible value for the type that you promised to plug in. Okay? Right, we already said the theta there, just in general. Theta is some sort of mapping from type variables, variable to reducibility candidates, right? That's just some environment that I'm threading around. And then what about the meaning of a judgment? Okay, so the meaning of the judgment now had some free type variables in it, E of type tau. So what's the meaning of the judgment when I say this? So what do I expect that to actually mean, right? Somehow E has to live in the meaning of tau for like, if I plug in something for all of the free references. Right? It's kind of like the same thing as before. So what do I plug in? So I'll say, for all theta, which is one of these things, right? And for all sigma, which has got to be one of these things. So I'm just kind of like extending the previous definition to say what happens if there's type variables as well as regular variables. then what do I expect? Well, it should be that E lives in tau. E, I plug in sigma for whatever the free variables are, lives in tau, where I use little theta for interpreting type variables in tau. You kind of see this appear again, right? I've got a program, and it's like got some generic type variables in it. So I pick some collection of syntactic types to plug in for those. But then also off to the side, I pick some like semantic interpretation for those same type variables in the result. And those things don't have to have anything to do with each other. But that's what I want to prove anyway. All right? It's that same like very strong statement that the types that you pronounced in your program to say what you're doing have nothing to do with what you're really doing. Okay? Does that kind of make sense what this definition is?
Do you have a subscript theta on the
Thank you, yes. Yeah, it's like for the most part, it kind of just threads around. It's like an environment. Yeah, so I was missing that, right? So every time I'm using these square brackets now, I need to like say what my mapping is for type variables. It's this bureaucratic detail that unfortunately you have to deal with. Just to like make that definition up there is well defined. Like the only time this matters is these two cases. And everything else it just threads through because nothing else is really binding or using type variables, right? Okay, and that's like also another ingredient if you're doing denotational semantics. You have this environment of what do I mean by variables, and you thread it around everywhere, and it very rarely gets used. All right, so now let's look at the two typing rules for a polymorphism, for the for all. And it mirrors again the case with functions, where when I was doing here, right, for functions, the application was really easy. And we'll kind of see that in the world of well-typed things is actually honest, right? Because like the world, the like room full of honest people is much smaller than like the room full of people who are allowed to lie and no one's checking, right? So we're checking that you're honest, but you're included among the people who might be completely fabricating things. But that doesn't matter, right? We don't care if you're honest. It's sort of like, I'm going to be pessimistic and assume you're lying to me. But it's okay that you're not. So here, the typing rule for using a for all said, well, let's say we have some free type variables, and I've got some generic E, which is for all alpha tau, and then I've picked some sort of type, tau prime, which is a type, and it's just some good syntactic type. And then I want to instantiate E, I guess I don't need E1, just E, at the environment theta gamma. E at tau prime, and I get something that lives in with tau prime for alpha. That's what I want. Okay. Yeah.
Difference between type star and member of type.
I'm saying something about the free type variables of tau prime. That's so. Remember the way, at least I should set it up, for well-formed types, and this was pretty much just saying it's a type that makes sense in this environment. So every free variable of tau prime exists in theta. That's really all I'm checking here. So a lot of presentations won't have that premise. In some sense, it's just like pick a syntactic type, but then you like need to say something weird about free variables somewhere else. So it's pick your poison.
But there's no meaning to switching between like a set notation and like a
No.
star.
Well, no. Actually, so a good thing. Let me do this. I can say something else here, which is you can assign a very sensible meaning to that, which is the meaning of that is going to be, so I'll say that here, rewriting it, the meaning of big theta on its own is going to be the set of all substitutions theta which live in, type variable, the mappings from type variables to CR, just sort of to keep this like denotational feel, like that makes sense. And so here, like this little theta lives in big theta, right? Which doesn't really say anything extra, but I might as well say that. So little theta lives in big theta. And then sigma lives in, so I'm not really changing the definition, I'm just being a little bit more, notationally pedantic. As what happens if I type check a term? I say something about where it lives under substitution. This was another judgment I had, which is that one right there, is a type in some environment. And what should that say? Like, that makes sense when, for all theta, little theta in the meaning of big theta, right? So I'm interpreting type variables as these reducibility candidates things. Then the meaning of tau under that interpretation little theta does indeed live in reducibility candidate land, right? And so that's another way of stating this theorem here, except more generally, right? I might have free type variables. So a better way of saying, like this lemma is a soundness for types, right? Like this is the fundamental lemma for types, which we proved before. We just weren't very clear on what we were doing. We're just well, types have to have these properties when I interpret them. And so the fundamental lemma of types looks exactly the same. It says if tau is a good type, right? It's syntactically checked. Then if this is derivable, then the meaning of that judgment, big theta, entails that tau is a type, is true, which says that when I interpret tau, no matter what little theta I pick, it is a reducibility candidate. So another way of thinking of this is if I think of this as an actual entity, like the kind of a type, and there are systems where I have more than just one thing there. It's not just it's a type, but there's higher kinds and type functions and things like that. You say, what is the meaning of a kind? So if I only got one thing, there's only one definition, but that's the meaning of star is reducibility candidates. And taus that I've got in my language are some of those reducibility candidates. Right? Might not cover everything, but at least cover some of them. So figuring out what the heck for all does makes it much more clear what types are, because in order to quantify over something, I need to know what it is. I can't quantify over something I'm completely clueless about. So doing polymorphism teaches me what types are better, because then I know what is all the types, what is that as an entity. Okay, let's keep going. Here we go. So, we do this. So right, we have to show something, we get an inductive hypothesis. So what are the inductive hypotheses? So I'll write it using this sort of consistent meanings of judgments ways. So the inductive hypothesis is that theta and gamma entail that E is type for all alpha dot tau, and that's true. And theta entails that tau prime is true. They're both true, which is to say, when I interpret tau prime at any environment little theta, that is a reducibility candidate. And I get that. Does that make sense? That's the inductive hypothesis. Okay. I have to show that this theta gamma. Instantiated at tau prime happens to live in the meaning of tau with tau for alpha. Right, that's what I've got to show. So suppose, right, so now we have to like introduce all the quantified things, right? It's for all various kinds of substitutions and mappings. So suppose little theta lives in the meaning of a big theta, which is it's just a mapping from type variables to reducibility candidates. And I've got some sort of syntactic substitution which lives in the meaning of big theta gamma with respect to that. And like this is the requirement that these two things go together, right? There is this chain of dependency. I introduce little theta and I use that to then introduce a sigma. Okay, it's like the flow of information. And now what do? I've got to say that, E instantiated at tau prime, here just expanding this definition from over there, that if I substitute sigma into that, which is defined to be the same expression as E with sigma substituted in for free variables and tau prime with sigma substituted in for its free type variables. That's the definition of that substitution operation. That's got to live inside of the meaning of tau with tau prime for alpha, interpreted with respect to little theta. I'm expanding that definition over there. Not really like doing any reasoning. It's just definition expansion. Okay, how do we do that? So the real trick is there's an extra lemma you'd want to show, which says essentially that when I plug in something in the syntax type, it's the same thing as threading it around in that environment theta. Right? So I kind of like want to pull out that right there. If I do, then that matches exactly my definition up there. Right? So as a lemma, say you want to show that tau with tau prime for alpha. I interpret that in theta. That is exactly the same definition as interpreting tau all on its own, where I instead put the interpretation of tau prime in the mapping theta. Right, so it's like, can I pull out this substitution, which is done syntactically on the tree representing a type, and can I do that substitution semantically in the interpretation of types? Are those compatible? Yeah. How do you show that? Any guess how you might show this kind of thing? How is the substitution defined? By induction on that type tau. That's how you define substitution. It's the same you define substitution for expressions. We saw you do the same thing for types. So you just say, well, for every case this works, and therefore it works. And that's not too surprising. That's like a usual kind of lemma you've got, that if I've got some interpretation that substitution in both the source and the target are the same. Does that make sense? Okay. So then that means here, right, this was the syntactic substitution. Here I can pull that out, and I've got that these two are the same thing, tau, and I've got theta with the interpretation of tau prime for alpha. So it's like as an exercise, do this, because I won't show you that. It's a good exercise, like all these inductive proofs to get practice. So these two are the same by that lemma, which you should prove for yourself so you believe it. These two are the same just by definition. Okay, so do I know this? Is this true? Why is it true? So I get to assume that E lives in the meaning of for all. What's the meaning of for all? That I get to pick any type and any reducibility candidate, and E instantiated at that type lives in that sort of thing. Right? So we're just kind of like pattern matching definitions right here and saying, like, does everything match? And you say, well, is this a reducibility candidate? Yeah, that's an inductive hypothesis. And is tau prime with some substitution a type? Yeah. All right, so that works. It works because of this hypothesis. Right? And it happens that the type I said I was going to use and the type I did use were the same, but that didn't matter. That was irrelevant. Okay? All right. So that was that step. Now, what about the hard one, which is I introduce polymorphism? What happens then? So what if I've got some sort of big lambda thing that was like a generic thing. So I've got a big lambda alpha dot E. That's got to be some sort of polymorphic thing. And all I'm doing is adding a free type variable to my environment. Okay. All right, so that was just the typing rule for introducing a big lambda. Remember, it works pretty much like a function, but instead of a regular variable, it's a type variable. All right, so what's my inductive hypothesis? So what's always my inductive hypothesis for this lemma? That's whatever that means, it's true. Whatever it happens to mean. So we're like arranging these definitions so that these are useful. So the meaning of this alpha gamma E of type tau is true. And now show that the conclusion is true, which is that thing. So show that that alpha dot E for all alpha dot tau, show that that is true. Right? So let's expand what that means. I have to work for some sort of generic, interpretation of type variables as reducibility candidates and some generic substitution. And if I do, then this works. Okay, so suppose, you kind of get this tedious, we keep suppose I have some generic thing and then plug it all in and you show that yes, because I plugged it in, right? I assume these work for anything, so it works for these particular things, right? So suppose I've got some little theta, which lives in big theta, and sigma lives in the interpretation of the environment. Right? What do I have to show? That when I plug sigma in for E, or for this whole thing inside of E, then it lives in the interpretation of that. Right? So show that the big lambda under my assumed substitution, and that just goes inside, right? Substitution distributes over every expression except variables. So that is equal to, for all alpha E, where I plug in sigma, that's got to live in the interpretation here. So that's got to live in the meaning of for all alpha dot tau using little theta. Okay, so what do we have to say here? Well, first we have to say that this is terminating. Is this terminating? Yeah, because it's a lambda and it doesn't do anything on its own. But then the second thing is you have to say if I introduce some random type and some random candidate, that it works, right? So you say, well, let me introduce some random tau prime and some random C, which is a reducibility candidate, but I don't know much else about it. Okay, what do I do then? Let me continue over here. do I do then? So, well, really all I can do is use my inductive hypothesis about the body, right? So first of all, I want to say, well, if I apply big lambda alpha dot E, I guess it's still the substitution sigma. If I apply that to, does something happen? Well, that can take a step, right? That can take a step. Take a step 2, E with sigma and tau prime for alpha. Okay. Do I know something about that? Well, if I knew, well, theta is a mapping, and also theta extended with C is another mapping, that's fine. And, well, is this a sensible meaning for that, right? So if I extend, right, sigma with tau prime for alpha does live in the meaning of theta gamma. Why does it live there? Because, well, I plug in something for alpha. I don't really care what it is, right? I didn't really have any requirements other than there was something there. Okay? So this is a valid substitution. Here is theta. Oh, sorry, I forgot to extend this. This is C for alpha, right? That's the, no. That's what I have to show, right? And I want to show that is it the case that this is in tau with, theta C for alpha. Is that the case? Well, I know that E is something with a free type variable. It doesn't really matter what I plug in here, like that is the inductive hypothesis, right? This is a special instance of my inductive hypothesis because I just picked some substitutions. It doesn't really matter what they are. Therefore, I know this is true. Does that make sense? Just plugging in this for the interpretation of some type variables as reducibility candidates, that for the substitution in the syntax of the expression. So that's true, and therefore by expansion, this is true. How theta C for alpha. And that's what I had to show. That's my obligation, essentially that it didn't matter. And it doesn't by the inductive hypothesis, right? Like nowhere did I care that those two things are related. So I'm done with that case, right? And so like that's the parametricity thing, is you set up the ability to lie and you show that your notion of polymorphism is so strict that you don't depend on the type to know what you're doing, and therefore it doesn't matter whether or not you're telling the truth. Okay? All right. So very quickly, so do we kind of get that? Like before we wrap up, I want to say one fun thing. So this is like I used this relation. I set up reducibility candidates to prove termination, but that's just like one theorem you'd want to prove. And so there's this thing that's called free theorems, which is like I proved this general thing, which is the fundamental lemma. Can I extract interesting things from that without doing a lot of work? And well, one of them, I'll show one of them, and this is related to when Jan was doing the encodings of things, which is sort of, he showed like, here's an encoding of like unit and product and sum, and they work in the sense that when I write my program, they reduce to the correct thing, but they don't have sort of the extensional property, which you might refer to as a universal property. Like for unit, right, the definition, the unit in system F was for all alpha, alpha arrow alpha. So that was like the polymorphic identity function, right? And you'd want to say that that's like a unit, but it's a unit because there's only really one thing I could write. Clearly I could write the identity function. Can I write something else? And so that would be a free theorem, right? Free theorem, which is I've got some closed term of that type for all alpha, alpha arrow alpha, then, and I'll write it this way, E is beta eta equal to the identity function, which is big lambda alpha little lambda x of type alpha x. And so by beta eta equal, I mean apply the beta rule for like the reduction rules anywhere, but also use that eta law I showed you earlier, and you'll kind of like have to like expand it to get it to go. Free is maybe a little misleading because this requires some amount of cleverness, and that's why these are tricky. And like in it, like how does this work? Well, you say, this is well typed. The fundamental lemma tells me that E lives in the interpretation of that type. And that gives me liberty to pick any darn thing I want for alpha as long as it's a candidate, which is a pretty easy thing to come up with. I have to come up with any set of terminating things that have expansion. I can just expand things by definition. That's not hard, right? So like the trick is, so the proof, this isn't like the full proof, but try to like fill in all the dots. The proof is that from the fundamental lemma, we know that E is in the meaning of for all alpha, alpha arrow alpha, and then here I'll say epsilon, which is like an empty mapping. It just like maps everything to the empty set. So the empty set is one of the reducibility candidates because everything it contains, which is nothing, is terminating. And if I had something, then I could have more stuff, but I don't have anything. All right, so that's one of them. Okay, so I know that. And now I get to pick some sort of thing to plug in for alpha. And like the trick is you pick, well, x, that's a set that just contains the free variable x. That's not a reducibility candidate because, it's not, it doesn't have that expansion property. But this does. That is a reducibility candidate. Why? It's got expansion by definition. Everything terminates. And then you plug that in for alpha. And then that tells you that E must be beta eta equal to the identity function. So there's like nothing else it could be. And like free theorems are hard because like you have to do this trick of saying that something's polymorphic is an extremely strong statement, and that means I can pick weird things, and if I pick a really good thing, I learn something interesting. So that's the hard part. So like as an exercise, see if you can kind of like put the things together and use the fundamental lemma to do that. But that's kind of like the side note on why I set up the things that I did the way I did. Like I kind of knew I wanted to do this. And this is really easy if I'm allowed to like run programs with free variables in them, as long as I don't like get caught and have a problem. And because I can just say, well, that's a reducibility candidate. We're all good. And then that gives me this really easy free theorem. Once you've figured that out, at that point it's just like unfolding definitions and running the term. All right, so like this is kind of like how the logical relations and the idea of reducibility generalizes to polymorphism with candidates and lets you prove some useful things about programs and like that, and in particular all those encodings work. So when you encode Booleans, the only possible things it could be is true or false, right, as functions. Those are the only possibilities. The encoding of numbers have to be the numbers. There's no other option. So that means those encodings actually make sense. So I think I'm going to wrap up there because we're a little bit over. I covered what I wanted to for this. So yeah, if there's a question. And correct.
Why don't you extend theta?
Did I typo it? Oh yes, I typoed right here. Yeah. Yeah. I forgot that. But that's also true. Yeah. Yeah. So that was the fact that I needed, and I forgot to write that extra detail. But yes, that is also true for like the same reason. And yeah. And it, yeah, it kind of doesn't matter in that sense, what it is, because what's the trick? Tau prime doesn't have a free alpha in it, so it doesn't matter what we put there. Does that make sense? So tau prime, wait, no, actually, no, it doesn't matter because we don't interpret those things. So yeah, it's not related. But yeah, so that was the, this is sort of what unlocks your inductive hypothesis. To use an inductive hypothesis, I have to come up with some good substitution, and that unlocks some good result, and then I can use that. And so that was the correct one, yeah. Okay, so that's it. Thank you for coming to the foundations of programming languages that is the prequel to the rest of the summer school. I believe a lot of people are staying, so I'll still be around if you've got some questions. You can ask me questions in the next couple of weeks.
Yeah, I think she said it all. Thank you so much for your patience teaching us. I've got this linear resource here, and I'm going to make use of it. So thank you very much.